I don't know why this is not showing up on my screen, so I'm going to have to use my computer. Hopefully this records, so make sure you're taking notes. What was the last thing that we talked about? We were just about doing a spirometry, weren't we? So there's a picture of, let's see, slideshow. I think this is where we started, right? No, I'm going to record lab today, so you can go back and listen to lab. So we're not going to cover the same information twice. But in lab, I did say that you needed to know how to run a spirometer. You need to know these 4 lung volumes. So anybody remember what the normal breath is if you've had lab already? It's called tidal volume. The tidal volume is just the normal you breathe in, breathe out. What's the amount beyond tidal volume that you can breathe in? It's extra, so it's called, what are you doing? You're inspiring, inspiratory reserve volume. And then everything to blow out beyond tidal volume would be blowing out candles, right? It's reserve, it's extra, so it must be blowing out is expiratory reserve volume. What's the amount that you can never push out of your lungs? You blow everything you can out. I plug your nose, your mouth, take an x-ray of your lungs. What's left in your lungs is called the residual. You can't get it out. It's stale air that stays trapped in there. There we go. And then I just went through those. You have to know the 4 volumes. You'll need to know them for the exam, too. The 4 lung, and I don't care about the values. The only value you'll probably really ever see again is maybe the tidal volume. A normal breath in, normal breath out. 500 milliliters. That's 1/4 of a 2-liter bottle worth of air. The capacities, what makes the volumes different from the capacities is the capacities always overlap volumes. They're adding at least 2 volumes together at any time. So your inspiratory capacity is your normal breath in, plus it's that inspiratory reserve, that extra breath you can take. So let's say you take a breath in, and something tickles your throat. What do? You either cough or like this, right? So if I breathe in like this, that tidal volume plus the inspiratory reserve is my inspiratory capacity. That's the amount I can breathe in. What if I breathe a normal breath out? I breathe in and then Is there any air left in my lungs after I relax my breath? Yes. There are 2 volumes that are left, right? The expiratory reserve that I could push out in case of emergency, and what can I never push out? Residual. That's the functional residual capacity. That's the ERV plus the RV. So when you're looking at these capacities, they overlap. The next one is the vital capacity, the living capacity. If I want to try and completely inhale and completely exhale as much as I can, I move 3 volumes. My normal breath, so here's my normal inhale, and then my inspiratory reserve. If I start from this, completely inhaled, by the way, what's this volume called? With everything I can possibly hold in my lungs is in there. What's that capacity? That's my total lung capacity. All 4 volumes, I'm holding as much air as I possibly can in. Now I'm going to take and put a balloon up to my mouth, and I'm going to blow up as much as I can in one breath. I completely inhaled in, and then I blow. I blew out my inspiratory capacity, or my inspiratory reserve. That went my tidal volume. That went my expiratory reserve. All 3 of those volumes into that balloon are called my vital capacity, the amount I can move for life. For lab next week, you should be able to identify these different things on a graph. Just saying. So when you look at this, if you overlap the values or look at the values, I can't use a mouse today because my computer won't let me do that. But if you look at these different values, the IRV on the top doesn't overlap the TV. See how they come up to each other, but they don't overlap? And then the TV doesn't overlap with the ERV. They touch each other, but don't overlap. And then the RV touches the ERV, but it doesn't overlap. The volumes don't overlap. Look at all the capacities, though. So the first one, the IC, inspiratory capacity, are the top 2 volumes. IRV plus TV. The FRC at the bottom are the bottom 2 values. So ERV plus RV. The total lung capacity all the way here at the right edge is everything you can inhale completely. You take the deepest breath you possibly can. Everything in your lungs is your total lung capacity. What was the vital capacity? I told you, imagine blowing into a what? Balloon. So everything you can blow into a balloon in one maximal breath. We test this in lab. Functional expiratory volume is how much you can push out in 1 second. So the FEV1 is how much you can push out in a second. If you're under 80, they say you have a respiratory dysfunction. We don't know which one yet, but we can say that you have some kind of respiratory dysfunction. You're not able to get the air out fast enough. FEV2 is how much you blow out in 2 seconds. FEV3 is how much you blow out in 3 seconds. So it should be at least 80, at least 90, and then at least 97% are the typical values. The respiratory dysfunctions, I told you 2 major groups that we'll talk about in lab, and I'm sorry if you haven't had lab yet, but you'll hear this twice now. So the first one's an obstructive lung disease. Obstructive means they can't get the air out efficiently. When you listen to these people, when you're listening to somebody with asthma, what are you hearing them do? What do you mean gasp? Are they trying to get more air in? They're getting more air in. What are they not doing? They're not getting it out. You're hearing them breathe in, right? Inhalation. But you're not hearing the outward. So when you're trying to push out, they're having a problem doing that. What's preventing them from blowing out? Too much resistance, because what happened to the radius in the bronchioles? They got smaller. The bronchioles constricted. The radius went down. The resistance went up. And what happened to the flow? It went down. So the same concept we talked about before. So asthma is a good example of an obstructive lung disease. And we'll talk about it in lab. The other one that I want you to jot down, or actually there are 2 that you can jot down. One's emphysema, and the other one's bronchitis. Both of these, the people have a problem getting the air back out. Bronchitis, you can think of it kind of as a situation like asthma. They have lots of mucus and lots of inflammation in their airway. If the airway is inflamed, it's going to squeeze down to that hollow opening. It's hard to squeeze out and push the muscles away, so it squeezes down. What's it do to the radius? Makes it smaller. What's it do to the resistance? Makes it bigger. What's it do to the flow? Makes it down. Yep, lower. And then emphysema has nothing to do with the airway. Emphysema is actually about the size of the alveoli. Their problem is they can't get air out. What did they lose from smoking all those years? The elasticity in their lungs. Their lungs don't collapse the way they should. So they take a deep breath in. Their lungs are really compliant. They can take a deep breath. That's where they get that. How do you describe their chest? Barrel-chested, right? They get this big chest, but the problem is they can't get the air back out. So their elasticity is gone. They have to forcefully exhale every time that they breathe out. So they go, and if you watch them, they do what with their lips? They purse their lips. They're pushing out. They're constantly using what extra muscles to breathe out? The internal intercostals and the abdominals. If you contract the diaphragm, what does it do? It lengthens your lungs, right? So they can't contract the diaphragm for exhalation. They constrict the abdominal muscles and the internal intercostals to try and collapse their lungs. You're using muscles. A normal, healthy person like you, do you have to use your muscles to breathe out? No, you just let go of the muscles. They elastically collapse and push the air out. Now you know that. All right, and then restrictive lung disease means that they're restricted on how much they can breathe in. A perfect example is pulmonary fibrosis. Pulmonary says lungs. Fibrosis means what's going on around the lungs. Scarring. Yep, so they have this extra fibrous tissue that's like scar. Is it very flexible? Nope, so it doesn't expand very well. Is it very elastic? Doesn't snap back very well. They can't expand and they don't snap back as easy. Right? So it's like putting a lead vest on you. You can feel that pressure on your chest. You feel like you can't expand it, and it's restricted. It's a lead vest. It doesn't flex. Right? So you can only go to the extent of that vest. What's going to happen to their total lung capacity? It decreases. Yep. What about the obstructive lung disease? Their total lung capacity stays the same, but they have a problem getting air out. What's going to change the most? The stuff they can't get out. No, which value on the chart? It's the residual volume. The residual volume, if you look at it, look at that RV on somebody with obstructive lung disease. That RV before was about 1,200. Now it's at 2,500. They can't get that air out, which, like you said, is filling up with CO2. When you look at somebody with restrictive lung disease, what's changed dramatically here? Their RV is a normal one, about 1,200. What's changed the most? Look at their TLC. It's dramatically lower than the average person. Okay, I'm trying to figure out how to run this without a mouse. Okay. Next thing you need to be able to calculate is pulmonary ventilation. Pulmonary ventilation is just like cardiac output. Cardiac output was heart rate times the amount of blood you push out in one heartbeat. Pulmonary ventilation, respiratory rate times the amount of air you push out in one breath. What's that air called? Tidal volume. So pulmonary ventilation is easy to calculate. You take tidal volume times respiratory rate. If the normal 70-kilogram male has a 500 milliliter tidal volume and they breathe 12 times per minute, their pulmonary ventilation is 6,000, which is 6 liters. That's 3 2-liter bottles of air that they're breathing every minute. That's not the best calculation for good air getting down into your lungs. Because you have to remember that everything from the tip of your nose all the way down to the alveoli is anatomical dead space. It's dead air. What are you not getting during that space? Thick tubes. What's the whole purpose of getting the air to the alveoli? Exchange. All the way through the anatomical dead space, there's no exchange. You can't get it through. When it comes into your nose, it doesn't penetrate the wall and go into the blood. When you get into the pharynx, it doesn't penetrate the wall and go into the blood. When you get it down into the larynx, the trachea, the bronchi, the bronchioles, no exchange. This is all wasted air. Like I was saying the other day, that's why I thought, geez, it would make more sense to have a nose right in the middle of your chest, because the air goes straight in and it's all good air. You got all this like foot to foot and a half of dead space going up to your nose. That's wasted air. Every time you breathe out, you have to push that bad air out, which actually, by the way, is unused air. So you're pushing it out to get fresh air back down. So when you look at the air coming down in, you can see it flowing down in, but that 150 milliliters up at the top, there's no exchange because it's not in this round alveoli. There's nothing happening with it. So to get a better estimate of what's going on in the lungs, what do you have to do to your tidal volume? Think about it. Get rid of that dead space. If your normal breath was 500 milliliters coming in, get rid of the dead space. That's not getting down to the lungs. So you take the tidal volume 500, subtract 150, and it comes out to 350. Then you take a times respiratory rate. And that comes out to about 4,200, so about 4 liters. So that's about 2/3 of what we bring down past our nasal nares. And then if you really want to get picky, that space actually has some dead space in it too. Because if you look inside this alveoli, anything that doesn't touch the walls is not used. It didn't get exchanged, so what do you do with it? You blow it right back out. You brought it in, you blow it right back out. This is a problem with emphysema because their alveoli aren't teeny tiny like yours. Their alveoli are huge, gigantic, which means what happened to that dead space in the alveoli on someone with emphysema? It got bigger. When you look at their overall surface area, because you have less alveoli, you actually decrease the surface area. It's like that whole aorta to capillary story I gave you before. You have one aorta that's like 1 inch wide and it covers about 4.5 square centimeters. But when you look at all the capillaries, even though you can't see them with your naked eye, they cover about 6,000 square centimeters worth of space. There's a huge difference in the surface area between those two structures. It's the same thing here. Somebody that has healthy lungs, they've got all this space. If you flatten out your lungs and you're a good, healthy person, your alveoli will cover the surface area of roughly a tennis court. So that's a lot of surface area. When you take somebody with emphysema, if they take 10 of these alveoli and pop them and turn them into one big one, that's 1/10 of the surface area you had before. So even though they're big alveoli, the surface area collectively is a lot smaller. That's some of the things you want to remember about diseases. Something like emphysema, you look, oh, look at how gigantic their alveoli is. Man, that must be really useful. Wrong. Totally wrong. Not only did you not get a good exchange in it, but what's it not doing anymore? It's lost its elasticity, so it can't get the air out very well either. You get a lot of carbon dioxide building up in there. And like I said the other day, when you build up carbon dioxide, what else are you building up? Acid. So somebody that has chronic emphysema, what's happening to their blood acidity level? It's becoming more acidic. It's constantly becoming more acidic, which is going to screw with their brain, which we'll talk about later. All right, so we talked about alveolar dead space. In lab, I talked about the garden hose story, so if you haven't had lab yet, there's something to look forward to. Okay, let's see, we talked about this in lab too, so local controls on smooth muscle airways and arterioles. What you really want to pay attention to are the 2 words at the end of these sentences here, the bronchiolar and the arteriolar. What's controlling your bronchioles according to the sentence? Carbon dioxide. What's controlling the arterioles according to this second sentence? Oxygen. Which one's carrying blood? Arterioles. Which one's carrying air? Bronchioles. Your airway is controlled by carbon dioxide. Your bloodway through the lungs is controlled by oxygen. The primary determinant of your breathing is actually carbon dioxide. Oxygen's having an influence on the blood flow, but not the breathing rate. If I put you in a room full of CO2, real high CO2, but you have plenty of oxygen, you start getting panicky. You start freaking out. You start breathing differently because of it. You start breathing heavier. Even though you have plenty of oxygen, you've got all the CO2, it makes you freak out. Conversely, if I put you in a room that's just fine with the CO2, but it has zero oxygen in it, guess what you do? You're fine. You're like, man, you're really tired. And then you pass out and you die because you don't have oxygen. And I looked for this pig video and I couldn't find it, but it's funny because there's a video on pigs. This is strange because they take a pig, they put a little clear plastic box with a box of apples inside of it. So the pig can see this box of apples. Pigs love apples. And then they can put their head inside this plastic box through this little hinged door, and they can eat the apples. They took one box and it had just fine oxygen, 21% oxygen, but the rest of it was CO2. The pig put its head in there, started eating an apple. It ate half of an apple, freaked out, spit the apple out, and pulled its head out of the box. It was spooked. It was like, what the heck's going on? It freaked out because it had high CO2 levels in there. It could detect the CO2. It was building up in its body and freaking it out. What was wrong with the oxygen in that box? Nothing. It got plenty of oxygen. That didn't freak it out. Then they took another box, and what was interesting is that they took that other box and they made it completely free of oxygen, but they put the perfect level of CO2 in it. The ideal level of CO2. The pig stuck its head in the box and started eating. It had no oxygen. What did it do? It was eating the apple, got tired, and it was like a little kid trying to feed himself while they're falling asleep, and it just fell over asleep. Luckily, it fell over, and its head fell out of the box, so it laid there for a few seconds, and it popped up and looked around. It's like, what the hell happened? And guess what it did? Went back to the box. So there was no oxygen in that box, but it kept going back to it. The primary determinant is CO2, not oxygen. When you look at oxygen, what's oxygen controlling in your lungs? The blood flow. This is tricky too. If you have low oxygen in a muscle, what do the arterioles do? They open up to carry more oxygen in, right? If you look at the lungs are exception. The whole body except the lungs work on that low oxygen, vasodilate. If you have low oxygen in the lungs, the lung blood vessels will constrict, which seems totally counterintuitive. If you have low oxygen in the lungs, that's a low oxygen percentage. That means what's happening to the rate of diffusion if you have a very low concentration of oxygen? It slows down. What do you need to do to the flow going through to be able to pick up the appropriate amount of oxygen? You have to slow the flow. If you slow the flow, it gives more time for these little oxygen molecules to jump on the hemoglobin. And I use this example in lab, and I always use this example. It's like if you are an oxygen molecule and you're on the interstate and you want to get a ride. Do you want the cars going by 50 miles an hour? Or do you want them going by 1 mile an hour? 1, because 1's just barely moving. You can open the door and jump right into the red blood cell, right? So when this blood vessel constricts down because of low oxygen, it slows the flow so the oxygen can jump on really quick. And then it speeds up when it leaves the lungs again. So it's kind of an important concept you want to make sure you're paying attention to. Right? And then gas exchange of CO2. The whole purpose, actually, where do you get exchange, by the way? Capillaries, or in the lungs it's called the, so the alveoli and the capillaries. So we're talking about the pulmonary capillaries in the lungs. It's always at the alveolar level, not the bronchial, not the bronchi, not the trachea, none of those things. All right, so the whole purpose of gas exchange is to pick up what and get rid of what? Pick up oxygen, get rid of CO2. And the two places to do that are at the capillaries. Pulmonary capillaries and systemic capillaries. Pulmonary capillaries and systemic capillaries. And then how it moves, it's not active transport. How do little teeny tiny particles move in your body? Diffusion. Yep, passive diffusion. No energy required. The air that you breathe is not the same as the air in the environment. The air in the environment is about 21% oxygen, but as you're bringing air in, you've got all that dead space. You can't just dump everything out and then bring fresh stuff in. It has to mix with that dirty air in the dead space and then come down into your lungs. So as you're breathing in, you're mixing with everything that's in the dead space, but you're also saturating that air with water. Why are you putting water in the air? To keep your lungs from drying out, right? If you walk outside today, it's really dry outside, it's really cold. What happens to your hand? It gets dry, right? Really dry and looks nasty. If your lungs experience that air, what would they do? Your skin is hundreds of cells thick. What would happen to that one cell alveoli? It would dry and die. It would dry and crack. You don't want that to happen. So you're constantly mixing with warm air, moist air, so that you can keep those lungs in good shape. When you look at the values, you want to pay attention to two numbers in general, and they're both revolving around what's in the lungs. Your P, partial pressure, is what that stands for. Your pressure of oxygen in your lungs is about 100 millimeters of mercury. The important point about this is that if you want the oxygen to go from the lung into the blood, what do you know the concentration of the blood's oxygen has to be? Higher than 100, the same as 100, or lower? It has to be lower. So as long as the partial pressure of oxygen in your lungs is 100, it's going to go downstream into the blood and go into the hemoglobin. That's why when you have somebody that's having a problem getting oxygen into their blood, you put a nasal cannula on them. You don't shove it in their nose and seal it off, right? You just let a real high percentage of oxygen go up into their nostrils, because what's the oxygen going to do? High concentration in their nostrils goes to their pharynx, down to the larynx, the trachea, all the way down into the alveoli. So what do you do to this partial pressure in their lungs? You raise it. If you raise the partial pressure of oxygen in their lungs, what's it do to the speed of diffusion? Increases it. You're getting it into their blood faster. Like people with emphysema. You're putting more oxygen in their lungs, so you try and displace the carbon dioxide, and the oxygen goes faster into their bloodstream. So the whole purpose is that you're trying to get that fast rate of diffusion. And then the second thing is the CO2 in the lungs is about 40 millimeters of mercury. Outside, it's less than 1%. It's actually less than 0.1%. The CO2 in your environment is extremely, extremely low. Very, very low. If it's at 40 parts in your lungs and it's like nothing outside, where does it want to go? It wants to go outside, slowly or quickly? Very quickly. It's like putting 500 people in this room and putting one person in the hallway. You're going to go really fast out of this room to where it's very empty. That CO2 moves really quickly. And the good thing is that if you pull it out of the lungs really quickly, it can move from where into the lungs quickly? From the blood into the lungs quickly. So you want to pay attention to diffusion. This is the same concept we've talked about probably 100 times since the first day of class. When you look at this, you can doodle in your head a little picture. You can see the 100 up there in the lungs for the partial pressure of oxygen, the 40 for the partial pressure of CO2. Look at the blue side over on the left side of the equation there. I don't know if I have a laser pointer. Sure I do. If you look over here, look at the oxygen. The oxygen's 40. Or no, it's not. Yeah, it's 40. That's right. So I'm having a hard time seeing it at an angle. Where's it going to go if it's 100 in the lungs and 40 down here in the blood? Oxygen goes into the blood. This is the deoxygenated side, right? Until it hits what? What's it trying to hit? Equilibrium. So now it's 100 evenly here, then it goes out into what? What's going back towards the heart? Venules, veins, chambers of the heart. Any exchange along here? Nope. And then to the, what's next? Artery, arterial, any exchange? Nope. And then to the systemic capillaries. Any exchange? Yes. Here it's 100 parts oxygen. Here you're constantly burning oxygen. I can't move that thing, sorry. It's constantly burning oxygen, so you always have low oxygen here. It's going to go from the blood into the tissue, right? So what's going to happen to this number? It's going to drop until it hits equilibrium with that low number. So now I only have 40 parts oxygen in my blood. It gets carried all the way back up. I have that 40. What's going to happen here? More oxygen comes in. You keep going through that cycle over and over and over again. CO2 is exactly the same way, but reversed. You pick up the CO2 down here at the systemic capillaries. You carry it up to the lungs, where you can see it at 46 here. It's 40 there. Where's it want to go? It wants to go out and into the lungs. And then it goes from the lungs out into the atmosphere. Right? So diffusion again. Same concept we keep talking about over and over and over again. Whose concept was that? Fick's. And Fick said, and here are two properties you have to remember with the lungs. Number one, the larger the surface area, what happens? Greater diffusion. Young, healthy lungs have large surface areas. Old, emphysemic-ridden lungs, what happened to their surface area? They decreased. Went down. What happens to the rate of diffusion at their lungs? Decreased. The thickness of the membrane. When you have mucus buildup, buildup. Remember cystic fibrosis where they can't move the chloride, so mucus accumulates in their lungs? What's that doing to the thickness of the membrane? Thicker and thicker and thicker. So you get the cell membrane plus this big wad of mucus on the side. What's going to happen to the rate of diffusion when it's thicker membrane? Slower diffusion. Makes it harder to move. So the next major concept, and this is where we actually are picking back up. Yeah, Tiffany? Exercise enhances the rate of gas transfer by increasing the surface area. You take deeper breaths. What'd you just do? Yeah. Okay, and then gas transport. The two gases you want to pay attention to do not move the same. All right, oxygen, physically dissolved in the plasma, the fluid in the blood. Only 1.5% of the oxygen that moves through your body is in there. Not enough to keep you alive. It needs hemoglobin. So these hemoglobin molecules are the primary carriers. The oxygen gets into the hemoglobin. It sticks to what little metal? Iron. It sticks to the metal, that heme group that has the iron. So you can hold on to those 4 oxygens per hemoglobin, 1 billion hemoglobins, or oxygen molecules all together in one red blood cell, and you transport it. That's how it moves. So why is anemia so significant? Why is it so dangerous? It's decreasing the amount of hemoglobin or the effectiveness of the hemoglobin. They can't carry oxygen any other way, really. When you look at carbon dioxide can actually likes water a little bit more. It can physically dissolve in the plasma. It can bind to hemoglobin to a different part of the hemoglobin, not the heme. But only 30% of it will bind to the heme, or the hemoglobin, I'm sorry. So the bulk of carbon dioxide does not move in the hemoglobin. The bulk moves to something called bicarbonate. So you go through this chemical reaction where you take CO2 and you have to turn it into bicarbonate, and that bicarbonate moves through your system. When it gets to the lungs, it turns from bicarbonate back to CO2, and then you blow the CO2 out. They're moved by 2 totally different mechanisms. So reduced hemoglobin. Reduce means we've taken the oxygen away. Reduce is a chemical term. When you've oxidized something, you add oxygen to it. When you reduce it, you take it away. When you oxidize your metal on your car, what did you just do to it? You rusted it. So oxidized means that oxygen hit this thing and actually chemically changes it. When you have oxidized iron on the heme, it's called oxidized hemoglobin or oxyhemoglobin. Reduce means there's nothing. What color does it turn when it's oxidized? Which color does the hemoglobin turn when it's oxidized? This reddish-orange color, right? This brilliant red color. When it's reduced, what color does it turn? This like purpley color, like this deep purpley burgundy color. So when you're looking at the light bouncing off of this in your eyes, what color does it seem under your skin? When it's reduced, it looks blue, right? When it's oxidized, it looks red. So when somebody's turning blue, it means their circulation is just fine, but what's their problem? They're not getting oxygen into the blood, right? If they turn pale, that means their circulation reduced. You're not seeing anything in there, right? You're not seeing the red oxidized blood. You're not seeing the blue deoxidized blood. You're not seeing any blood. So when you turn ghostly pale, what just happened to all those blood vessels in your skin? They constrict it and squeeze the blood out. So you need to know the difference between oxy and reduced. This term hemoglobin saturation means exactly that. When you saturate something, great, my screen's jumping all over the place. When you saturate something, what do you do to it? You fill it up, right? Ah, crap. We may have just lost my computer. What a day. All right, let's see if I can get back there. Tell me when I hit the slide that you're on. I'm further forward. Right there? Okay, so we're talking about hemoglobin saturation. I'm going to go ahead and stick right here for a second. Because the only thing that we missed was the word hemoglobin saturation, right? And you have it in your notes. It doesn't have it in your notes? It means it's saturated. When you saturate a sponge, what's it tell you about a sponge? You filled it completely with water, right? So you saturated the sponge. When you saturate hemoglobin, what did you just do? You filled it with what's trying to carry? Oxygen. One hemoglobin can carry 4 oxygen molecules. Saturation of hemoglobin means you're binding to all 4. What's kind of cool about it is that it's this chain reaction. When you unbind one, it makes the other 3 kick off. When you bind one, it makes the other 3 come back on. It's kind of a cool process. So here's where it's significant. If you didn't have hemoglobin, you wouldn't be able to carry oxygen because only 1.5% of the oxygen will mix with the water. So what's happening is you're basically carrying oxygen sponges through your blood so that you can carry this oxygen. So you've got all these little hemoglobin molecules. If you look at the numbers up here it looks like 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that 10? I can't see it at an angle. So if we say there are 10 particles here, and then how many particles do you have in the plasma here? You only have 2 in the plasma. Look, you have 1, 2, 3, 4, 5, 6 bound here to the hemoglobin, but those are not in the plasma. They're in the interstitial fluid. These are inside of a cell. Based on the properties we talked about diffusing things with the extracellular fluid, where's the oxygen want to go in this situation? Sorry, there are 8 there, and then there are 2 here and 6 there. It goes from the lungs into the plasma, right? Because diffusion is pulling it from this chamber to this chamber. And then it goes from the plasma to what? Into the hemoglobin. As it's pulling into the hemoglobin, what's it doing to the plasma concentration? Reducing it, which always makes it look lower than the lungs, right? So what is oxygen always wanting to do? It's always going to go from the lungs to the plasma and then the plasma to the red blood cells. If you didn't have hemoglobin, look what happens. You diffuse this until it was at equilibrium, but these things aren't comfortable there, so they're going to stay there. They're not going to move very well. So this is really cool. If you take this situation here and you just pop those hemoglobins into it, look what you did to all that free-floating oxygen. What'd you do? You just pulled it into the plasma and then stuck or saturated all of your hemoglobin so you can maximize your oxygen-carrying abilities. Look, what do you call the plasma versus the lungs right now? They are equilibrium, right? Is this at equilibrium? Nope, because these little hemoglobin molecules are like magnets. They don't care about equilibrium anymore. They're going to constantly pull all the oxygen you will give it. It just keeps pulling and pulling and pulling and pulling. I don't think that'll work on mine either. When we talk about the percent hemoglobin, we're talking about what percent of the hemoglobin is actually saturated. It's not very often you actually get 100% saturation. You can get 100% usually when you put a nasal cannula up to somebody and you start cranking oxygen into their blood. Yep. So you're going to have between 0 and 100%, and usually it's around 90%. So it's pretty high, but it's usually rarely completely saturated. Usually it's around 90%. Right? Because you're always using that oxygen in your blood. Whether it's heart muscle, skeletal muscle, the brain, whatever, you're always using some of it. It's hard to keep it 100% saturated. How this moves, this deserves a little star, but it's the concept you want to understand. It's called the law of mass action. If you've taken chemistry, they call it Le Chatelier's principle. It means if you have some kind of a chemical equation like this, so just look at the Hb, which means hemoglobin, plus oxygen equals oxygenated hemoglobin. If I take hemoglobin, introduce oxygen, it oxygenates the hemoglobin, and I have this oxygenated hemoglobin. This rule says that if I add things to this side over on the left, this equation has to carry through and increase the side on the right. If I decrease the side on the right, that means that this side has to start changing and shifting over to the right. This principle says that if I increase something on the left, the equation shifts to the right. If I increase something on the right, the equation shifts to the left. If I decrease something on the left, the equation shifts towards the left. If I decrease something on the right, the equation shifts to the right. It will always keep shifting so that this stays nice and balanced. This is the best analogy I can give you because I hated this when I learned chemistry. I thought, what the heck? How can I make this easier? I imagined a bathtub. I have a little bathtub that starts here, comes all the way over and then up. Over here I have a faucet. Over here I have a faucet. Over here I have a drain. Over there I have a drain. If I pull the plug over on this hemoglobin side and I reduce the amount of hemoglobin I have, what happens to the water level in that bathtub that goes all the way across here? Does it just go down by the hemoglobin? No, it all goes down. I'm pulling the water out this side, but that means the water on this side of the tub also has to reduce with it. Does that make sense? That's the easiest way I can give you explain it. What if I turn the water faucet on over here? What if I turn this faucet on and it's dumping hemoglobin and oxygen into my blood? What's going to happen to the water level all the way across here, this tub? It raises on this side too. Does that make sense? It doesn't matter which side you turn the faucet on or pull the drain on. Both sides have to change equally to each other. It's called the law of mass action. We're actually going to use that later when we get into acids and bases a lot too. So a couple weeks from now. Okay, so oxygen hemoglobin dissociation or saturation curve. This is an interesting curve. So when you, actually I'm going to just jump to it. When you bind oxygen to hemoglobin, it's not for every oxygen or hemoglobin you have, you bind to an oxygen. There's actually a change in speed depending on how full you make the hemoglobin. So that's why it has this weird shape. They call it a sigmoid curve or an S-shaped curve because it's not straight up. It's not like I add one oxygen and it binds to hemoglobin, add another one it binds to hemoglobin, add another binds to hemoglobin. It actually will bind quickly in the beginning and then it starts leveling off and then it gets slow at the end. The way I always thought of this is that when I was a kid, I loved field trips. Where did you stand in the line for the field trip if you love field trips? You stand at the back of the line to get on the bus or the front? Right? I stood right at the front because why? The ones at the front always get the best seats. You can jump up on the bus. In fact, I'd run up on the bus. I'd go running along. I look and I'd find the seat and sit down. What's wrong with the very back of the line? You always sit by the stinky kid, right? So, because nobody else wanted to. At the back of the bus, you notice that the bus starts filling really quick at the beginning, right? They open the doors, and everybody goes piling in, but as you're getting towards the end of the line, what happens at the speed of filling that bus? It slows down. Hemoglobin is exactly the same thing. It's hard to find those seats when the bus is almost full. So, when hemoglobin comes up to the lungs nice and easy, or empty, so I'm bringing that red blood cell, it has 250 million empty seats on it, right? When I first come into the lungs, what's going to happen to those seats? Fill slowly or quickly? They fill quickly. They fill really, 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 really fast. And then now that red blood cell is getting full, what's happening to my rate that I can actually find empty seats on the red blood cell? It decreases. It gets lower and lower and lower. So, unluckily, if my blood's moving really quick through the lungs, what's happening to those last seats? They're not getting filled at all, right? Which goes back to when you have low concentration of oxygen, what happens to the flow to try and get more seats full? You slow it down. You spend more time in the lungs. You constrict those blood vessels, right? So this is called the saturation curve. This is how fast oxygen jumps on. What's interesting is that when it gets to the tissue, it works exactly the same way. So when you get to the destination, the first ones empty off the bus really, really quick, and then the last ones are like, staggering along, waiting to get down. They're like plugging up the aisle. They're clogging the aisle, waiting to get off. So can you completely empty that red blood cell at the tissue? Nope, you're going to, unless you stop the blood. The only way to do that is to break the capillaries. Hit somebody in the arm with a baseball bat, the red blood cells aren't moving anymore, right? What's going to eventually happen to the oxygen in all of those red blood cells? It all leaves. So what color does that tissue turn? Like a purpley color, right? And you're seeing the red blood cells that are deoxygenated or reduced sitting in there. They've dumped all of their oxygen off. They can't get any new oxygen. They're stuck. And then eventually they get broken down to bilirubin, which turns yellow, jaundice, and then they get cleared away. So this curve, the big picture with this curve is that at the very beginning, when the red blood cell moves into an area, what happens? Diffusion is at its fastest. You get really, really fast diffusion, and then at the very end, what happens to diffusion? It slows down. Okay, so it's not consistent the whole time. When you're looking at this, these factors are really important. They say that factors that shift the curve to the right or the left. The ones that shift the curve to the right will actually speed up movement of oxygen. So if I have an increased CO2 in that area, that CO2 is like a bully. It goes into the bus and starts pushing all the oxygen out. So what's it doing to the rate of oxygen emptying? Speeding it up. If you shift the curve to the right, you empty the oxygen faster. Does that make sense? The big CO2 bully comes rushing in and starts pushing all the oxygen off the bus. Would that be a good thing? It would be a good thing if you were at the systemic tissues, right? Why? Why would it at the systemic tissues? Why would you want CO2 to push all the oxygen off? Because you want the oxygen to go into the tissue. Right. You want the oxygen in the tissue. So when you have high CO2 in your muscles because you've been metabolizing energy, it goes into the red blood cell and actually kicks the oxygen off and pushes it into the tissue. Does the oxygen like to hang out in the plasma? No. 1.5% binds or mixes with the plasma. The rest rushes right into the tissue. So raising the CO2 will actually raise the rate that you empty the bus, which is a good thing. The second one, increasing acids, H+. When you're metabolizing, what are you accumulating in that muscle? Lactic acid. Lactic acid's presence does what to the emptying of the bus? Speeds it up. It kicks lactic acid, just like the CO2, goes in and it pushes all of the oxygen off. The acid actually binds to the heme. It sticks to the heme and just pushes the oxygen right off. Is that a good thing at the tissues? Absolutely. When you get the systemic tissues, it's kicking the oxygen off so it goes into that metabolizing muscle. It's trying to push the oxygen into the muscle that's metabolizing. Right, and then the next one, increased temperature. When you're metabolizing the muscle, what happens to its temperature? It goes up, remember? 75% of it's used as heat. If you're not moving it and you're metabolizing, it's 100% heat, remember? So, in other words, those first three things, the way you remember this is all three of those happen when you're doing what? When you're exercising, right? You increase the CO2 in the muscle, you increase the acid in the muscle, you increase the temperature in the muscle. All three of those things do what to oxygen getting out of the hemoglobin? Speed them up. It pushes it out of the hemoglobin so it goes into the tissue faster. Is that a good thing? Isn't it amazing how our bodies have developed? All these little things that are happening, and they have to happen. Otherwise you would die. So all this machinery we've learned about so far this semester is just a miracle. Right? Next, this one, the increase 2,3. I think in your book it says biphosphoglycerate in your notes. It's biphospho. They mean the same thing, it's just the letters changed. So instead of di, which means 2, it's bi, which means 2. But biphosphoglycerate, sometimes it's abbreviated BPG, 2,3-BPG. B as in boy, bi. This is an interesting one too. You have this in certain parts of your body, and it increases the curve to the right, which means it does what to oxygen leaving that red blood cell? Increases it. Where you're going to see the significance of this is when we talk about reproduction. This is really high in the placenta. Why? It's trying to get oxygen out of mom's blood and into the placental blood, right? So they can get into the embryonic blood. It's trying to move it because mom still needs to stay alive, right? She's carrying oxygen. Her tissue's using the same amount of oxygen as always used. But what's left on that hemoglobin, the placenta is going to go, we need everything we can get. It releases this stuff onto the blood and it dumps the oxygen out so it can go into the placenta faster. So all four of these things all together do what to the curve? They shift it to the right, which does what to the speed of emptying? Increases the speed of emptying. So what would happen if I decreased all of those? It would decrease the speed of emptying. It would slow the emptying. So in colder temperatures, what happens to your ability to move oxygen out into the tissue? It slows down. The diffusion of oxygen slows down in those temperatures. And then this is the picture where it just shows it shifting to the right. I'm not going to put a graph on the test, so you don't have to memorize the picture. You have to understand the concept of shifting to the right. This last one, shifting to the left, this is one thing, carbon monoxide. This is interesting. Carbon monoxide, it's not trying to kick the oxygen off faster. What it's doing is it's preventing the oxygen from binding. Carbon monoxide gets right onto the heme, sticks to the heme, and prevents it from binding. On the hemoglobin. It prevents it from binding the hemoglobin. So when you're up in the lungs, you're trying to bind oxygen to the hemoglobin, but if there's carbon monoxide, what's it do? They say that carbon monoxide has a higher affinity for hemoglobin, about 250 times higher affinity. Do you know what affinity means? If you really love someone, you have a high affinity for them, right? If you love chocolate cake, you have a high affinity for chocolate cake. If I like chocolate cake, and you like it 250 times more than I do, who's going to get the cake? You are. You will knock me down, you will beat me to death, and you will get the cake that you want. See, carbon monoxide, CO, is exactly like that with oxygen. You can put the same amount of oxygen and the same amount of CO in the room. Which one's going to bind? CO. It doesn't matter if you have plenty of oxygen in your environment, because what's happening? The carbon monoxide binds to the hemoglobin, and it absolutely positively refuses to let go. It just holds on. So it will hold on and it will never come off. What do you have to do to the red blood cell now? You have to destroy it. You're going to have to destroy the red blood cell to get rid of the carbon monoxide. So when somebody's in a house that has carbon monoxide in it, and what do? They start going, God, I feel really uncomfortable. I feel, oh man, I just feel like you can't. They don't turn blue.
My sister did.
Cherry red.
They turn cherry red. Why do they turn red? They turn red because where is the carbon monoxide binding? To the heme. It's oxidizing the heme. What's it doing to the heme? It's rusting it. It's turning it bright red. So when they die, they look kind of red and pink in the face. Jack Kevorkian, I think everybody still remembers who he is, right? So Jack Kevorkian, when he would euthanize people, he liked doing it with carbon monoxide because he said, well, in their last days, they looked all pale and gray and really, they looked really dead already. So by giving them the carbon monoxide, it actually brought life back into their face. It made them look more alive when they died. Oh, that guy was something else. It's amazing how you can justify doing something like that. No, he's dead. Yeah. I can't say you don't. Not that I know of, but you shouldn't have carbon monoxide. You have lots of carbon dioxide. Yeah. So then she wasn't getting oxygen. It's not the carbon monoxide that would turn you blue. It's the lack of oxygen that turns you blue. But if it's carbon monoxide that did it to her, then carbon monoxide, when it binds to the hemoglobin, turns it red.
Yes, so the carbon monoxide was up in that juice for her lips turned blue, and then she got sick and right away the doctor said she was allergic to carbon monoxide. So my mom called her the carbon monoxide detector. She had passed out. But that's from that movie, and that's because of...
It's the turning blue is because you're not getting oxygen into your lungs, period. If it was turning blue, then the carbon monoxide wasn't binding either. Because if carbon monoxide binds, it turns red. Maybe she was holding her breath and just turning blue in the face. Okay, so carbon monoxide, when it goes in, it just prevents oxygen from binding, so you can't carry it. When somebody's exposed to carbon monoxide, they leave the house, you actually tell them, stay out of the house for a couple days. Why? Well, they turn the fans on, they pump the CO out of the house, they have somebody come in and they fix it, but why do they tell them, even with all the windows open, why do they not want to be back in the house? Why do they want to be in an area that has high oxygen, a nice, normal environment? Because all that red blood cells are gone now. They're still floating, but they're worthless. They're not doing anything. So the kidneys have to have a chance to make more erythropoietin, which goes to the red bone marrow and makes more reticulocytes, which makes more red blood cells. Exactly. You want to give it some time. You make 5 million a second, but that still needs time to replace the carbon monoxide bound ones. So shifting the curve to the right and the left. If I asked you a question like this, which factor shifts the oxygen hemoglobin dissociation curve to the right? So, how about a cold temperature? What's that do? So, cold temperature, it doesn't technically shift it to the left. It just does what to the rate of unbinding? It slows down the unbinding. It doesn't shift it to the right. Warm temperature shifts to the right. How do you remember that? How do you remember warm temperature shifts it to the right? Because exercise warms your tissue. What about carbon monoxide? Does it shift it to the right?
Left.
That shifts it to the left. How about low acid environment? So a very basic environment. Right. The pH scale, that's a tricky one. We haven't talked about acid base yet. But if you have a low pH, it's very acidic. But if you have a low acid environment, it's very basic. So it's saying that you have a basic environment. Does that shift it to the right?
No.
What environment shifts it to the right? An acidic environment. And then how about number 4, increased partial pressure of CO2? Yes. The more CO2 while you're metabolizing, the faster the oxygen jumps off. So the big picture there is remember what shifts to the right and to the left, and you want to think if it shifts it to the right, it makes oxygen do what faster? Jump off the hemoglobin, get off the hemoglobin bus, and move into the tissue faster. If it shifts to the left, what's happening? It's not allowing oxygen to bind, right? So it's preventing oxygen from binding. What's the only thing that shifts the curve to the left you need to know? Carbon monoxide. Monoxide. Okay, so we talked about how oxygen is transported. How is 98.5% of oxygen transported? stuck to, yep, hemoglobin, the heme. Carbon dioxide, what was the number one way you move that? By turning it into this thing called bicarbonate. So turning it into bicarbonate. So remember, this was on a slide before. Physically dissolved, about 10% just mixes with the water in the plasma. Bound to hemoglobin, about 30%, and they call it carboaminohemoglobin. It's actually binding to part of the globin molecule and not the heme. So that's why it doesn't act like carbon monoxide and block the oxygen. It just bullies the oxygen off. Right. The 30% sticks to the hemoglobin, yep, to the protein part of it. And then the last part as bicarbonate. And it never fails. It always seems like that pops up on tests. And I'm not saying that because I'm saying, hey, guess what? I'm saying that, but when I took the MCAT, it was on there. When I took my physiology class in grad school, I took my physiology classes in undergrad. It was always on a test. This must be important. What is the primary carrying form of carbon dioxide? It's bicarbonate. And guess what the other answer on that test will always be? Hemoglobin. Yeah. Because they want you to think like, oh, it's exactly this. Those tests are meant to say, do you really understand the concept? All right, so here's a chemical equation. For the sake of this class, when you see a chemical equation in your mind, what should you draw around it? Little bathtub, right? So you have this little bathtub that comes from here, down, and over, and up. Yep, I talked about the law of mass action. Because when you see something like this, it's going to ask you, how does this stuff work? I'm not going to put the numbers in front of it, like if you took chemistry class and make you balance the equation. Screw that. This is about concepts, right? Not math. So over here, you want to think on this side, how could I possibly add CO2 to this side? Okay, turning the faucet up, right? So physiologically, how are we turning the faucet up in your body? How are you gaining CO2? Metabolizing more, right? So by gaining CO2, metabolizing more, or you're holding your breath. Those are two ways to increase this side of the equation. If you increase this side, what do you know has to happen here? It goes up. What about here? It goes up too. So remember, if you add something to this side of the tub, it flows all the way across and it raises every section of this tub. What if I start breathing heavy? I breathe more CO2 out. That's pulling the plunger, right? What's happening to this level of the bathtub? It's dropping. What's happening to the middle level? It's dropping. What's happening to the end level? It's also dropping. I'm hoping this concept's sticking with you. Because when I tell you later, the lungs and the kidney, you're going to need to remember this. Let's say that I'm building up acid in my body. I'm getting a lot of acid over here. What's happening on this side? I'm also accumulating CO2. Sound familiar? If I accumulate more CO2, I'm accumulating more acid. Make sense? Yeah, we're not going into diabetes right now. Yeah. Yep, you're jumping into the more applied right now. Look at the basics here. So the CO2 and the H+. If you raise the CO2, you automatically raise the acid. Vice versa, if you raise the acid, you raise the CO2. What organ is going to be responsible for controlling your CO2 levels in your body? Primarily the lungs. Exactly. So when you see this bathtub, you're going to see this equation 3 more times that I can think of off the top of my head this semester. Think of the lungs over here. What's going to control this? CO2. If I want to raise the CO2, what do? What's my lung do? Stops breathing, right? If I want to get rid of more CO2, what's it do? Breathes harder. Over here with the kidneys, if I want to raise the acid, my kidneys will actually slow down function. If I want to get rid of more acid, what's the kidney do? Increase more function. What's it doing to the acid? What's the kidney doing? Common sense tells you it's making you pee it out, right? So you're getting rid of this over here by urinating it out. If you want to reduce or gain more acid, you just turn down your loss in your urine. If you want to get rid of more acid, what happens to your urine? It becomes more acidic. And we'll talk about that in acids and bases more. But here's the big picture. This last thing, the CA, it's called carbonic anhydrase. What's it tell you with the ASE at the end? It's an enzyme. When we talked about red blood cells, that was the enzyme, one of the 2 enzymes I told you needed to know. Carbonic anhydrase in the red blood cell and also that glycolytic enzyme. So this carbonic anhydrase will take CO2 plus water, it takes it, sticks it together like 2 pieces of silly putty and then smashes it into this one thing called carbonic acid. It's acid. You want to try and get that change right away. So this enzyme turns it to an acid, but then it's going to take it and split it apart into an isolated acid and an isolated base. Right? When you see, if you're taking chemistry, you probably already know this. When you see the positive, a lot of times this will indicate that something kind of acidic or has acidic properties. The minus usually means it has more of a basic property, typically, not always. Right? So I shift this equation over. Remember, I'm making more CO2 and water, so now I'm turning it into carbonic acid, and then I'm turning it into this free acid and this bicarbonate, which are easier to deal with. They're easy for me to deal with. So that HCO3 negative, by the way, what did I just tell you the name was? It's on this page. What did I tell you the name was? What did I tell you the name was? Bicarbonate. That's bicarbonate. So when you see this up here, it's bicarbonate. When you see this, this is a shorthand for saying this is a carrying form of what chemical? CO2. Here's how it works. So now we're going to take that equation and put a picture around it. If you just look at this side, at the alveoli, or just that side at the tissue, this is systemic tissue. We're going to imagine that's a muscle, skeletal muscle. The skeletal muscle is burning oxygen, right? What's it making? ATP, CO2, and water. As I accumulate CO2 and water, what do they stick together to form? Look at the last slide. Carbonic anhydrase, or carbonic acid. So the CO2 and this water come out here to the plasma. They go into the red blood cell and they find that carbonic anhydrase. Is it in the... Nope. Yeah, there it is, right there. Carbonic anhydrase. So the CO2 and water find carbonic anhydrase. They turn into this carbonic acid. That carbonic acid, you don't want that because it's hard to deal with. So what do? Split it, and you make a free acid and a free base. What was that free base called? Bicarbonate. Yep. The acid's kind of cool because the acid will go up to the hemoglobin and it will actually stick to the hemoglobin. The acid's kind of pushy. The more acid you have, what's it going to do to the oxygen molecule to what's hanging on there? Kick it off. It says, hey, you're in my spot, and it pushes it off. But it's not so lovey like carbon monoxide. Oxygen later can go, I want that seat back, please, and it can come back and get on it. For right now, you want to remember that higher acid means what's going to happen to the more oxygen molecules. They get kicked off. Did you already know that? Yes, you did. It shifts the curve to the right. More acid means you do what with oxygen? Dump it off faster. And that's what's happening. So this acid, as I'm pulling the CO2 and the water in here, is turning into carbonic acid. The free acid is going to kick the oxygen off of the hemoglobin, and then it binds to the hemoglobin. So it actually sticks to the hemoglobin. Oops, I went up too far. There we go. So that's the acid plus the hemoglobin. They stuck together. No longer is it the acid with the plus. It's not dangerous. If you ever take a chemistry class and you see an H with a plus over it, it's hydrogen. It has one thing in this world. It's electron. When it turns positive, someone stole its electron. If you were a child and you had one thing in this world, your teddy bear, and someone stole it, how are you going to feel? Angry. What do acids want to do when they're angry? They want to break stuff, right? So they want to destroy things. The only way to make it happy is to take and give it something that makes it satisfied. This hemoglobin says, you know what? I know you're lonely without your electron. Come on over here, let's cuddle. Okay? So the hemoglobin makes it all comfortable again. It's happy. So these two are happy, and they can just travel all through your system. They go all the way up to the lungs. When they get in the lungs, the acid goes, well, thanks for the trip. It leaves. What can bind that hemoglobin now? Oxygen. Now the acid has to be turned all the way back into carbon dioxide and water. So now you're freeing up acids. You're building on the right side of this equation. What's going to happen? It moves over to the left to turn into carbonic acid. And then from here it goes to water and CO2. The water and the CO2 actually go out to the plasma. They go into the lungs, and bye-bye. When you breathe out, you lose the water, you lose the CO2. If you want to test this, it's what? 20-some degrees outside. You walk outside, and you go, what do you see? You see water vapor, right? So you know water's escaping with it, and we already know carbon dioxide is blown out when we do that. So it's that equation. It's amazing how fast this moves, too. This equation happens milliseconds. As soon as this gets to the lungs, you have the acid disassociating from the hemoglobin, binding with the bicarbonate, binding with, or turning into carbonic acid. Disassociating, turning into water, CO2, moving across the red blood cell, moving into the plasma, moving plasma into the lungs, and then being blown out of the lungs, all in milliseconds. So faster than you can snap your fingers, faster than you could twitch your muscle in lab a couple weeks ago. So all that has to happen. When you get to the lungs, the acid turns into CO2 water and you blow it out. When you're at the tissue, your muscle is making CO2 and water. You turn it into this carbonic acid, turn it into the bicarbonate, you turn it into the acid, and then the acid's comfortably carried all the way to the lungs and lost. Now what you should ask yourself is it possible to become too acidic in your blood? Yes. Is it possible to become too basic in your blood? Yes. If you look at this equation, you've just bound up and you've made the acid comfortable. But what's not comfortable? The base. The base isn't comfortable if it starts accumulating inside the red blood cell. So if you look at the base, there's the base. It's going, man, there's too much base in here. It's becoming too alkaline. It's too crowded. The base is going to leave the blood cell. Here's the problem, though. When the base leaves the blood cell, it takes a negative charge with it. Remember when we were talking about membrane potentials? If you start losing that membrane potential, the cells are unstable. A red blood cell can't handle that instability. It's hard to make energy in a red blood cell. Remember, there's no mitochondria. So it can't turn on pumps as easily as any other cell. So what happens is when it pushes a negative charge out to keep life perfect, it either needs to push a positive charge out with it or bring a negative in exchange. And what it does is it kicks one negative out and it brings one negative in, chloride. So you have this chloride with negative charge, and it's called the chloride shift. So everything keeps electrically balanced. Again, all this is happening in milliseconds. All this stuff here happens faster than you can blink an eye. Chloride shift just naturally happens when you're using this equation, period. Yep. As soon as you make a bicarbonate, the bicarbonate is going to shift out and the chloride is going to come in.
So that's normal.
It's normal. Yep. And then it's going to be the exact opposite. When you get to the other area, it's going to have the chloride go out, and what's going to come back into the red blood cell? The bicarbonate. And then the bicarbonate is going to go back to that chain reaction again and get converted back into CO2 and water. So yeah, if you look at one side, you can see over here the bicarbonate's leaving. On this side, the bicarbonate's coming in. Over on that side, the chloride is going in. On this side, the chloride's leaving. It's constantly shifting depending on where you are. If you're accumulating this process here, you're accumulating CO2, water, carbonic acid, acids, and bicarbonate. If you're accumulating the bicarbonate that's not doing anything inside that red blood cell, you've got to kick it out. When it kicks out, the chloride comes in. When you get all the way up here and you're actually decreasing this equation, you're shifting it back the other way to the left so that you can blow out the CO2 and water, the chloride will race back out so the bicarbonate comes in. This is just about as chemistry-like as we get, except for when we talk about acids and bases later. Right. Not today. It'll be down with acids and bases. All right. So when you look at the systemic capillaries, you need to remember what's going on. Systemic capillaries are accumulating what? They're living cells. They're accumulating CO2 and water, right? So which direction does the systemic capillaries shift that equation? Does it make it go, oops, let me go back to the equation real quick. So the systemic capillaries, does it make it go this way to the right, or does it make it go over here to the left? To the right. Yep, so you're building up CO2 and water, you're shifting all that stuff over here to the right. Then you get all the way up to the pulmonary capillaries. When you get to the pulmonary capillaries, now you're losing CO2. You're actually pulling the drain on the CO2 side. So what's happening? So if I pull the drain plug over here, what's happening to this level? It's going down, which means what's happening to this side over here? It's going down with it. All the water is shifting over to the left and dumping out the drain. Does that make sense? I can't think of any other analogy for you. So hopefully that works. All right, and then we already talked about this chloride shift. As bicarbonate does one thing, the chloride does what? The opposite. As bicarbonate goes out of a red blood cell, chloride goes in. As chloride goes out of the red blood cell, bicarbonate goes in. That's the chloride shift. So the two main things you want to remember here are what's happening with that equation at the different levels. Build up CO2, the equation shifts to the right, so you make these byproducts. The chloride shift out, which is the second thing. Or sorry, chloride. Bicarbonate shifts out, which means the chloride shifts in. You get all the way up, you've carried everything, it's comfortable, flowing through the blood, it gets up to the lungs. When it gets to the lungs, it says, well, geez, there's low CO2 in the lungs. Let's go ahead and shift all that CO2 out. So it turns the bicarbonate back into the red blood cell, shifting chloride out. Takes the bicarbonate, sticks it to the acid that was riding along on the hemoglobin. Turns it into carbonic acid. That carbonic acid dissociates into CO2, water, which goes to the plasma, which goes to the lungs, and you exhale. Alright, I love, usually when you see some scientist's name on their thing that they labeled, it's always usually common sense, it seems like. But these are two sides of the same coin. So there's this guy, Bohr. He says that if you increase the CO2 and hydrogen levels, it makes the oxygen leave the hemoglobin. We already know that, right? You raise the CO2, you raise the acid, the oxygen leaves the hemoglobin, and it cruises on out into the tissues. Haldane says, nope. This is how it actually works. The oxygen leaves, and then the carbon dioxide and the acid come in. Who cares? They're both saying exactly the same thing, right? It's saying that when there's high CO2 and acid, what do you know about the oxygen? It leaves the cell. Yeah, it leaves the red blood cell and goes into the tissues. It doesn't matter which perspective you look at, it's the same process that's happening. So if I ask... Yeah, kind of like that. Who wrote a paper on it first? The Haldane or the Bohr? You have to know the concept for those two. Yeah. Yep, which is the same concept we talked about with shifting the equation to the right. Yeah, it's the same concept. All right, next, which is not an important step in carbon dioxide transport. So how about number 4? Calcium comes into the red blood cell to make the red blood cell electrically neutral. What shifts in? Chloride. Yep, so when bicarbonate goes out, chloride shifts in. So we know number 4 is wrong. In fact, what's wrong with, why can't you swap calcium for chloride? Calcium's a double positive, right? So it's totally different than chloride. It's not going to help at all. So number 4 is totally wrong. Number 3, bicarbonate leaves the red blood cell to buffer acids. Boy, that's a confusing one. I don't know. How about number 2 then? Carbonic anhydrase. Carbonic anhydrase converts CO2 and water to H2CO3, which dissociates H plus to HCO3. God, what is that? That is exactly that equation, right? It's just written out. Carbonic anhydrase, right? That little enzyme converts the CO2 in the water into carbonic acid. From carbonic acid, it turns into acid and bicarbonate. And then number 1, carbon dioxide mixes with water to form bicarbonate and H+. Is that true? Does carbon dioxide mix with water? Sure does. Remember CO2 and H2O. They bind together and then they shift that equation and they eventually become bicarbonate and acids. So we know 1 and 2 are right. If bicarbonate leaves the red blood cell, what will it want to stick to? Bicarbonate is a what? And I told you need to write this down. It's the primary base. Exactly. It's the primary base. What's a base want to stick to? An acid. Yep. So number 3 is a true statement too. It sticks to the acids. Now if you have free acids flowing through your blood, they can stick together. I just didn't tell you it out loud yet. Alright. But right away we already knew number 4 was totally wrong, right? Because the chloride shift. So what's the correct answer here? It's number 4. Yep. We're looking for something that's not an important step. Alright. Next one. Control of respiration. When you look at this, you already know. Can you breathe without your brain?
No.
Nope. Can't breathe without your brain. What part of the brain do you have to have? The brain stem. What part of the brain stem do you have to have? Medulla. Yep. And here's why. And this is kind of cool because in pathophys, I just got done talking about this. How when somebody comes in and they have swelling in the brain, you can watch their physical symptoms. If you remember back from the nervous system, we talked about the midbrain for reflexes, to auditory and visual. You shine a light in that person's eyes, if their midbrain's intact, what happens to their pupil? It constricts, right? If you shine a light in somebody's eye, that means that the swelling, if their pupil doesn't constrict, it means the swelling has probably smashed the midbrain up here. Right? So the brain has been smashing down, it's compressing this midbrain at the top. They lose that pupillary reflex. The next thing that they lose is their control of respiration. Not the fact that they stop breathing, but they don't regulate it. They don't fine-tune it. So which part is responsible for fine-tuning breathing? If that's the midbrain, the next part is the pons. You need to remember that the pons are there to regulate fine-tuning. If somebody has brain swelling and they've already lost their pupillary response and their brain smashing down on their pons, then you'll watch the breathing get really weird. They go, it's called Cheyne-Stokes respirations. They lost the fine-tuning of breathing. They're breathing because they absolutely have to. They absolutely have to get rid of the CO2. That's their whole purpose. This pons says, hey, the CO2 level's rising. Let's just breathe a little bit faster. Oh, there it went down a little bit. Let's go ahead and relax. So your breathing will go normal, might speed up a little bit, and then slow down a little bit. But you will not be able to hear it. You have no idea. You know what's funny? I noticed this weekend. You ever listen to somebody that's wearing headphones while they breathe? Their breathing gets loud and annoying, and you just want to strangle them, right? Stop breathing! Anyway, the pons here is regulating the fine-tuning. It's helping regulate based on what it predicts. So when this gets smashed, their predictive behavior is lost. The primary breathing center in the brain that controls basic instinctive breathing based on CO2 and acid is what? Medulla oblongata. If they take let's say a nail gun right to the back of the neck and it hits their medulla, I know, I come up with some really weird ones, and it hits their medulla oblongata, what do they lose the ability to do? Breathe. They could fine-tune it if they could still breathe, but it doesn't matter. They can't breathe. What did you just do to them? They're dead. Yeah, there's nothing you can do. It doesn't matter that their whole brain is in good shape. Their midbrain's fine. Their pons are fine. They just stop breathing and they can't breathe anymore. Right? They're a goner. Unless you put them on an actual respirator, they're gone. No. If you cut out the medulla, no, there's no coming back from that. In fact, if you have compression going through here, like the brain swelling and squeezing, what will actually happen is something called Durette's hemorrhage. The blood vessels right here in the medulla blow out. Yeah, and there's no coming back from that. That's gone.
So then you'd be considered dead?
You'd be considered dead.
Oh.
Yeah. All right, so control of respiration. When you look at it, the big picture here, the medulla is the main respiratory center. It is responsible for you breathing, period. What did I already tell you is the main regulator of breathing? What chemical? CO2. Now I'm going to make it a little bit deeper. CO2, if the CO2 goes up, what do you think happens to your breathing? You breathe heavier, right? What's also going up with the CO2? Acid. So I think there might be a question on the homework that says this. The primary determinant of breathing is actually technically acid. The reason that we stick it to CO2 is because acid is electrically charged. Can it move across the blood-brain barrier? No, CO2 is not. CO2 has no charge. It's nonpolar. It's tiny. Can it move across the blood-brain barrier? Yes. So when your CO2 accumulates in your blood, what's it going to do? Moves into the brain and does what with the acid in the brain? Raises the acid in the brain. When you blow out lots of CO2, what happens to the CO2 in the blood? It goes down. So what happens to the CO2 in the brain? It goes down because it goes out in the blood. So what happens to the acid in the brain? It goes down with it. All right. So that's one tricky thing about the homework. I know that might be a tough question on there. It's the acid. So if it says what's the primary determinant and acid versus CO2, you pick the acid. If it says acid and CO2, pick the acid and the CO2. But the little cells in the brain, in the medulla is part of the brain, right? That blood-brain barrier prevents acids from moving back and forth. They're charged. They have a positive sign on it, just like sodium, Na+, like chloride, Cl-. The blood-brain barrier doesn't let those things move across. The CO2 moves across. It raises, because of that equation we saw earlier, it raises the free acids, which makes the brain, the medulla go, whoa, there's way too much CO2, start doing what? Breathe heavier. That's why when somebody's lost the pons, there's no fine-tuning. The CO2 level rises in their lungs. It's going to rise in their blood. It's going to rise in their brain. What's the medulla going to say? Breathe heavier. They start breathing like this, right? As they're breathing really heavy, they're blowing the CO2 out. The CO2 is starting to drop in their lungs, but it hasn't dropped in their brain yet. Now it's going to drop in their blood. They're still going, ha, 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 right? Not until it lowers in the medulla does the breathing do what? So all this time, they're really blowing lots and lots of CO2 out, and then suddenly the brain's CO2 level drops dramatically. What's the medulla say? Oh, crap. Kind of overdid that one. So what's it tell the lungs to do? It doesn't even say slow down. It says stop. So they stop breathing. They're breathing really heavy. Ha, 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 ha. And then they stop. They just stop. But now what's going to happen when they stop breathing? CO2 is going to start rising in their lungs. It rises in their blood and starts rising in their brain again. And then they start, as it's rising in the brain, they're going, and they stop. Right? So it keeps going through this routine over and over again. The areas that are up here, you've got the first one, the DRG. The DRG is the primary area. It sends a signal down the phrenic nerve and down the intercostal nerve and does what to those two sets of muscles? Fire. It says fire. And it makes them contract. When you contract the diaphragm and the external intercostals, what happens? You breathe in. That's the spot that allows you to breathe in. If you lose that one spot specifically, there is no coming back. You can't breathe in anymore. The second one, ventral respiratory group, this is stimulated when there's an increased demand for ventilation. You start exercising, right? It's going to kind of predict a little bit. It goes, all right, well, the acid level is going up in the blood. Even though CO2 is not really changing, we're going to see if we can start adjusting some things. So this will actually stimulate the DRG to fire. So the ventral respiratory group. It starts firing faster and faster, faster, faster to make you breathe heavier and heavier and heavier and heavier. And then the last one, the pre-Botzinger complex generates the pacemaker activity. So that you have this normal normal pace. So they're constantly firing over and over. It gives some kind of auto-rhythmicity to a skeletal muscle, so that you might want to think it. That's the medulla. Next is the pons. What do you know about the pons already? Fine-tuning. So the pons, you have this apneustic center, which prevents abnormal breathing. So if the medulla is going too fast, the pons says, hey man, what the hell's going on? Slow down. Calm down. We're doing fine. And it helps say, this is cool. Just slow down a little bit. So that apneustic prevents abnormal breathing. It's fine-tuning your medulla. It's telling it what it should be doing at the appropriate times. And this is kind of cool too. The pneumotaxic center will actually send a stop signal down in the medulla, so that you can intentionally hold your breath. So they can actually stop the medulla from firing. It's kind of cool because you actually have centers here in the pons that if your lungs expand too much, they will send a signal to the medulla and say, stop breathing in. You're overexpanding. What could happen if you overexpand these alveoli? You pop them, right? So I remember when the big Wharton turbines first came out, and I was at Iowa State, and everybody was like, oh my God, the cows are freaking out, and they're dying, they're having heart attacks, and sheep are dying and having heart attacks, and whatever, the birds are dying and having heart attacks because they're stressed out about these things. Whatever, that's crap. But what they did find is that one animal did die more frequently. Bats. So birds, they're flying towards this thing, and what's funny is they do find dead birds underneath there, but the birds die usually right around sunset, right? Because what's happening? It's getting dark and they don't see it very well, and then they slam into it, and you find these big bruises, big hematomas on their head when they fly into it. Bats are smarter than that, right? Because bats don't look, it doesn't matter if it's day or night, how do they get around? They send that signal out. They predict small changes. They are not looking at insects, but they can catch an insect midair based on their sounds, right? So these bats are smart. They fly around the wind turbine, but the problem is that on the front side of the wind turbine, extremely high pressure. So as they're flying up to it, there's a lot of pressure there, and when they get down behind it, the pressure dramatically changes, and their lungs go and explode. So when you find these bats on the ground, they don't have a hematoma to the head because they didn't slam into the thing, but if you open them up, their lungs are just a mess, a bloody mess. They've exploded. There's your fun fact for the day. Yep. And then next, the inspiratory neuron pacemaker activity controls two nerves that you already knew about, the phrenic nerve and the intercostals. Remember when I talked about getting the wind knocked out of you? You hit the phrenic nerve, and what muscle doesn't work now? The diaphragm. If you can't send a signal down the phrenic nerve, you can't turn on the diaphragm. So that pacemaker activity starts here in the medulla oblongata, and the medulla will send a signal down and out through why am I having a brain fart? The ones that exit, efferents. Yeesh. Efferent neurons, and then they go, phrenic nerve goes to the diaphragm, and then what's the name of the one that goes to the intercostals? Right, the intercostal. So the intercostal nerve comes out here. So the signal comes down and causes the fire, and then as soon as it's contracted completely, that signal shuts off. This signal shuts off, and what's the diaphragm do? It relaxes. How does it move when it relaxes? Does it go down or does it go up? And it goes up, right? So it moves back into its arched position. Causes the lungs to do what in size? Shrink in size, which did what to their volume? Which did what to the pressure in there? Raise the pressure, which caused what to happen? Exhaling. Don't forget those different steps. And this reflex, the Herring-Brewer reflex, this is that reflex that I was kind of talking about, that you can't overexpand your lungs. So when you start exercising, there will be a cap to how far you can expand your lungs. You'll go and breathe as much as you can, but this reflex is preventing you from ripping your alveoli, tearing your alveoli. It's called the Herring-Brewer reflex. Right. So that way your tidal volume doesn't go over a liter. What's the normal tidal volume? About a half liter, yeah. Your rib cage, if I put a chain on your ribs and started pulling, I could pull your rib cage further than you can expand it out. Yeah. There was a saw moment, right? I'd rather not, since this is being recorded, but if I put a chain hook on his rib cage and I pulled on it, I could actually expand it further than he can consciously expand his chest. Yeah. Because there's enough flexibility in those muscles and everything, I can pull it out further. Yeah. There's a vivid image for you. Okay, and it's because you have pulmonary stretch receptors. You have receptors around the lungs that detect when the stretch goes too far, it says stop, this is too far. It sends a signal up into the pons in the medulla and says, this is it, and shuts off the phrenic nerve and it shuts off the intercostal nerves. As soon as you shut those two nerves off, what happens? The lungs automatically relax, right? So the skeletal muscle relaxes, it compresses the lungs, and you exhale. Involuntarily exhale. You just let it out. So it sends an afferent nerve up to the medullary respiratory group, and then stops the inspiratory neurons. So which control center in the brainstem is involved with fine-tuning? Which ones? So you're right, it's the pons. Which one of these falls into the pons? The last one, the apneustic. Yep. So the DRG, the ventral, and the preboscinglar group are all in the medulla oblongata. The apneustic is the only one that's not. Right. Chemoreceptors detect what? Chemicals. The chemical that we're focusing on right here are the peripheral and the central chemoreceptors that are sensitive to CO2, oxygen, or acid. The peripheral chemoreceptors are more sensitive to oxygen and carbon dioxide. And acid, actually all three. The central one, specifically two chemicals. One chemical primarily, but the other one is kind of by default. What's the central? Central is referring to what area, by the way? Brain, central nervous system. The central receptor, I told you, is most sensitive to what chemical that can't move across the blood-brain barrier? Acids. What's the other chemical that comes with it naturally? CO2. So the chemical chemoreceptors in the central nervous system are to acid primarily and CO2. Not oxygen at all. They could give a damn about oxygen. They don't care. Your brain is not very responsive to oxygen. The peripheral ones are going to be oxygen, CO2, and acid. And we've already talked about some of these peripheral ones. We talked about like the ones that are actually on the blood vessels or around the blood vessels in the lungs. They're sensitive to what chemical? The blood vessels. Oxygen. How about the airways? CO2. Yep. When you look at where the central ones are, of course, they're in the medulla oblongata. When you look at the peripheral ones, have you seen these before? Yeah. Carotid sinus and aortic arch. What else is hanging out there? What other receptors? Blood pressure receptors, which are called what receptors? Baroreceptors. Exactly. It's the same place as those baroreceptors. And then chemical regulation and ventilation. Actually, I'll just go right into these. There we go. So signals increased ventilation. If you have a low oxygen in the arterial blood, right? So in the blood supply, in the which central or periphery? What did I tell you about oxygen in the central nervous system? Doesn't care about it, so it has to be peripheral. So losing oxygen in the peripheral arteries, that's where you find these regulators. This is the weakest stimuli, period. When these things start firing and saying, hey, maybe we should start breathing, you're already passed out because you haven't had enough oxygen. So when somebody's getting CO2 poisoning, they're in this environment, they fall asleep, and then they start breathing heavier while they sleep. Because now the oxygen's going, hey, yeah, not very much oxygen. Let's go ahead and turn those receptors up. Next one, increased arterial partial pressure of CO2 strongly stimulates central chemoreceptors. What's the thing that can actually overpower the CO2? Acid. So number 2 is specifically at the central. Number 1 was specifically at the peripheral. And then number 3, increased acid in the arterial blood at the peripheral chemoreceptors. Where else do you know? Also at the central. Yep. So right below peripheral, right also the central. Remember, the central one's primarily controlled by the acid, but the CO2 is rising at the same time. So, what is the weakest stimuli of all 3 of these? The decreased level of oxygen. Yep. And then what's the most powerful regulator of breathing? The acids and CO2. Yep. In the lungs it's the CO2, and the brainstem is actually the acids. Right. And then I've got like 1 minute left, but here are some slides that show you. So if you have a arterial, looks like a drop in partial pressure of oxygen, what does it stimulate? Central or peripheral? It stimulates the peripheral chemoreceptors, which send a signal up to the brainstem and say, hey, maybe you want to start breathing, which would increase the ventilation. Is this a powerful response? Low oxygen in the periphery? No. All right. And then the next couple slides are just flow charts just like that. So I think this is one of the last slides, right? Increased 2,3 BPG would stimulate what? Would it stimulate the peripheral chemoreceptors, central chemoreceptors, or neither? What stimulates the peripheral? Oxygen and acids. Yep. What about the centrals? Acid and CO2? Neither. It's neither. Yep. And then nuts. Yeah, it's exactly 2:30. Sorry, I'm going to spend 1 of your minutes. I'm sorry about that. So these last things that profoundly increase breathing, right? We don't understand why exercise does this, but it's funny because as soon as you start moving your joints, you breathe heavier. It's slight and you don't really notice it, but you breathe heavier. As soon as your body temperature goes up, you breathe heavier. Right? You already knew that, though. As soon as epinephrine goes up, what happens to your airway? Inhale more. Yep. And then impulses from the cerebral cortex is telling you your subconscious or conscious? Conscious. Yep. So you can psych a lot. You get a little psyched out. What happens to your breathing? Your breathing goes up, right? So it's interesting, some of these mechanisms. I don't know. You have to look at the slide. Yep. So things like exercise, heat, yep. Thinking about it. And then voluntary control of breathing is the cerebral cortex because you're conscious. So that when you want to speak, you want to act, like sing, control your breathing, that's all conscious. When it's subconscious, it's always coming from the medulla oblongata. Thank you for that 1 extra minute. See you in lab. Good luck on the test on Tuesday. If you have questions, let me know.
So, lecture quiz today?
Yep, make sure your lecture quiz and your homework are done by Tuesday. Don't forget lecture quiz and homework are done. Yeah, I'll get on there tonight and open it up.